All right, previously in class we looked at series, or a partial sum of a sequence, and kind of looked at whether or not they would diverge or converge. And so we're going to look a little bit more in depth at two specific types of series, and that's geometric and telescoping. And then we're going to look at other ones as well. So these are two special series. And you should have heard of geometric already. So if you guys recall, that's just, we'd have a sequence where the pattern is that it's consistently multiplying by the same number. And so if you talk about it in a situation where it's a series, that would just mean that you're adding all those numbers together for that pattern. So for geometric, it's going to look something like the sum from, we'll go ahead and use 0, from 0 to infinity for the number of your terms of a times r to the n. So a would be the first term. That's what you'd get when you plug 0 in for n. And that would make this equal 1. So a is your first term. Your second term would be if you plug in 1. So a times r to the second, and so on. And then you'd have, actually put dot, 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 a times r to the n, and it would keep going forever because you're going off to infinity. So here, just to make sure that we remember everything about geometric series or sequences, r is the ratio, or the common ratio. And if that word doesn't make a lot of sense to you in this situation, you could say it's the number that you're multiplying by each time. These series diverge when the r value is greater than or equal to 1, and it could be the positive version or the negative version, it doesn't matter. So if it's a positive r, then you're going to be consistently multiplying by a bigger number, and your sum is going to get bigger and bigger and bigger, and it's going to diverge because the sum is going to go off to infinity. If you have a negative r, then your numbers are getting larger, and they're alternating between positive and negative, and again, they're going to diverge. So we're going to say it converges when the absolute value of r is less than 1, and that's because your numbers are going to eventually be fractions, and eventually that fraction is going to approach 0. And you should be somewhat familiar with this because you've already found these sums in the past. That's part of the pre-calc curriculum, or maybe even earlier. So we have a over 1 minus r, and the a value is your first term. Or if they want you to find the sum and they say from 5 to infinity, then you would start with the fifth term. You would just start wherever they tell you to start. So that's geometric. The other special type of series is telescoping, which you might not be familiar with. You might not have seen that at all, and that's okay. So I need to write series here. So a telescoping series, we're going to go ahead and say we're doing the sum from 1 to infinity, is b sub n minus b sub n plus 1. And you'll see in a little bit we'll do an example, and it will make a lot of sense how these are going to be pretty easy to work with. So what this means is that if I plug in 1, then I would have b sub 1 minus b sub 2. And then if I plug in 2, I would have b sub 2 minus b sub 3. And then if I plug in 3, I have b sub 3 minus b sub 4. And then it would go on forever. So what you'll notice is I'm subtracting b sub 2 and then I'm adding it, and those two are going to cancel out. I'm subtracting b sub 3 and then I'm adding it, those two are going to cancel out. I'm subtracting b sub 4 and then I'm going to add it, they're going to cancel out. So you'll notice that b sub 1 is going to stay. That never cancels out with anything. The other thing that's going to stay is whatever your very last term is when you actually plug that infinity in. So that's how telescoping terms work. So what that means is that most of the middle terms go away. And we're going to say this will converge if and only if, when they say in math, when they write the IFF, that's what they mean, if and only if B sub n, so that's that first term right here, if B sub n approaches a finite number. All right, so that means that the limit as n goes to infinity of B sub n has to equal a number, some sort of number. All right, and then if that is the case, then we're going to say the sum is B sub 1 minus the limit as n goes to infinity of B sub n plus 1. So that's exactly what I was saying here about this B sub 1 never gets to cancel out with anything. And then the other term that's left is whatever we plug in when we get infinity plugged into the second one. And so that's exactly what this is saying. The reason it's a minus sign is because the infinity would be the second term here. And that's why it's subtract, because it's minus. All right? So B sub 1 is the term that doesn't go away. Now here it could be one single term or it could be multiple things, but they're the things that eventually, if you wrote it out, you would see which ones they are. They're the ones that are not canceling. All right, so we've looked in the past at like properties of logarithms, we've looked at properties of exponents, we've looked at properties of limits now that we're in calculus, we've looked at properties of integrals, and so those are the types of things like different operations that still hold true. Now that you're not just adding or subtracting numbers, now maybe you're adding or subtracting integrals or something like that. So just like we've done before, we do have some properties of series, although only two. So here are the properties that we're going to look at. So we're going to say if the sum of the sequence A sub n equals A, and the sum of the sequence B sub n equals B, then here are the two properties that we're going to remember and use. Then the sum of some coefficient multiplied by the sequence A sub n is the same as if you take that coefficient out to the front and then just multiply it by whatever the sum of A sub n is. So it's going to be C times A. So that will come in handy. We've been doing that with integrals, right? If we have a number in the front, you can kind of pull it out and just work with the more simple version and then multiply it at the end. So this is nothing really new to us. We've definitely done it before. The other is the sum of one sequence added or subtracted to another is going to be just their actual sums added or subtracted from each other. So those are the two properties that we're going to work with. Okay, now when you are looking at series and you can see that it's geometric or telescoping, we're going to be able to see if they diverge or converge pretty easily because we have some specific things about them. But sometimes you have a series that doesn't fit either one of those situations. And so for those particular situations, you're going to do what we call the Nth Term Test for divergence. And notice this is only testing divergence. It's not testing to see if it converges and what it converges to. We're not there yet. So this is just to see if it diverges, if it's not telescoping and it's not geometric. So we're going to say if the limit as n goes to infinity of the sequence does not equal 0, then the sum of the series diverges. If the limit as n goes to infinity of the sequence does equal 0, then we have no conclusion. So either it diverges or we can't say anything. We don't know. All right, so here are some examples. We'll do a few in the video and then we'll leave some for class. And the instructions are going to say determine whether the series converges or diverges. If possible, find the sum. So determine whether the series converges or diverges. If possible, find the sum. So for our first example, we're going to find the sum from 1 to infinity of 1 over 2 to the n. So this doesn't fit the typical format for telescoping for sure, because it's not one thing and another thing. And it doesn't really fit the typical look of a geometric, but I can actually rewrite this. I can say that this is the same as 1 over 2 to the n, because 1 to the n, 1 to the first power, second power, third power, is always going to be 1, so it didn't really need an exponent on it, but it doesn't hurt if I do put an exponent of n on it. Now when I look at it like this is clearly a geometric function, sequence, because geometric sequences typically have some sort of number in the front, which in this case would be a 1, and then r to the n power. So now we can say this is geometric. We have an r value of 1/2. Now this r value is less than 1, and so that means that this series is going to converge. And since it converges, that means that I can go ahead and find the sum. So the sum is the first term, which is what I get if I plug 1 in, and that's 1/2, divided by 1 minus r. So 1/2 divided by 1/2 is 1. So it converges, and it converges to 1. Next, we're going to go ahead and find the sum from 1 to infinity of 1 over n minus 1 over n plus 1. So if you think about what the terms would be if you write this out, your first term is going to be 1 over 1 minus 1 over 2. Your second term is going to be 1 over 2 minus 1 over 3. Your third term is going to be 1 over 3 minus 1 over 4, and so on. So as you can see with this, negative 1/2, positive 1/2, those cancel. Negative 1/3, positive 1/3, those cancel. And if we did this forever, we would eventually have, the 1/4 would cancel obviously, we would eventually have negative 1 over 1 at the very end of this. Right? So if you think about that, if we keep the 1 over 1 in the front and we have a minus 1 over infinity at the very end that we're keeping, that's kind of like saying we've got 1 minus 0. So just thinking through this problem, I know that this is going to converge to 1, but I want to go ahead and show my work. So here is a telescoping series. And what we do is we check to see if the limit as n goes to infinity of that second part equals 0 or not. Or see if it converges. And it does. This converges to 0. So for us to find the sum, we're going to say that b1 value, which was 1, minus the limit as n goes to infinity of 1 over n plus 1, which was 0. 1 minus 0 equals 1. So again, the reason that I know that this telescoping series had to converge is because the limit of the second part was an actual finite number. It doesn't have to be 0. It just happens to be 0 in this case, but it does have to be a specific value. All right, let's go ahead and do a third example, and then we'll call it good for the video. So here we're going to do the sum from 1 to infinity of 1. Now this, there's no exponent of n. This is not geometric. It's not telescoping. So this is where we have to do that nth term test. So if you were to write out these terms, you'd say the first term, there's nowhere to plug in 1. So the first term is 1. There's nowhere to plug in 2 for the second term. There's nowhere to plug in 3. So you're just adding 1 repeatedly, right? So we're going to say this is not geometric or telescoping. That means that we have to do the nth term test. And the nth term test says take the limit as n goes to infinity of the sequence, which is 1. And I can't plug infinity in anywhere. So that means the limit as n goes to infinity, that's just 1. And this limit does not equal 0, so we know that this diverges. Remember, if it equals 0, it's inconclusive. We don't know what it means, but if it doesn't equal 0, it definitely diverges. And if you think about this, it makes sense because you're repeatedly adding 1, so your sum is going to get bigger and bigger and bigger. It's definitely not going to converge to a specific sum or a specific value.